Hello, 101C people. Okay, this will be your first asynchronous activity. So let me change to the writing board. There we go. So what we're going to do is talk about vectors in R2. When I say R2, what I really mean is the coordinate plane. Coordinate plane. So the x and y coordinate plane that you know and love, that's what we mean by R2. Just to tell you, R1 means the number line. So this actually should make sense. The number line is one line. You can think of the coordinate plane as two number lines, which is why it's called R2. Okay, so let's talk about notation. So today we're going to discuss things called vectors, particularly vectors in the plane. So a vector in the plane is represented by a directed line segment. So what do we mean by that? What is a directed line segment? So let's put a little axis right here. Okay, wait. Let's do that again. Redo. Came out blue. I don't like it when it's blue. There we go. Cool. So there's our coordinate plane with our x and y axis. So what do we mean by a directed line segment? Well, a directed line segment, first of all, is an arrow from an initial point to a terminal point. So we're going to choose a point, let's say 1, 2. So 1, 2 will be our initial or starting point. Okay, and then we choose a terminal point, the ending point. Let's make that a 4, 3. So that's our terminal point. Okay, so what's a vector? In the plane, you can think of it as an arrow which starts at the initial point and ends at the terminal point. So it goes like this. The arrow represents the direction because you could go the other direction, right? You could have a vector which goes like this. So you can have a vector that goes from 1, 2 to 4, 3, or you can have a vector that goes from 4, 3 to 1, 2. It's directed, so we actually distinguish between the two of them. It's not just like a line segment. Okay, so we have the direction. The length of the line segment is called the magnitude. So here we have our vector right now. We usually represent vectors with bold letters. So because I can't really bold very well, we put a little arrow over it. So V with an arrow over it means the vector V. This vector that starts at 1, 2 and ends at 4, 3. The magnitude is the length. In other words, how far it is from 1, 2 to 4, 3. We represent magnitude by writing 2 bars around the vector. So that's how you write the magnitude of that vector. Okay, so a vector is a quantity which has both a direction and a magnitude. Okay. You can have some sort of very interesting vectors. So what about the vector that starts and ends at the same point? So what about the vector that both starts and ends at the same point? So what's that? In other words, a vector where the initial and terminal point are the same thing. We have a special name for this. It's called the zero vector. And we have a special way of writing that. We write 0 with a little line over it. So the zero vector is the vector which both starts and ends at the same point. The zero vector is a little weird. It doesn't really have any direction. Because like if you had like a point over here, you could say, oh, that direction's like this. But there's nowhere, you can't draw the arrow for it, so by convention, it doesn't have a direction. It's a little weird. So, odd. Okay, cool. So we've got that so far. Scroll down a little. Two vectors are equivalent if they have the same magnitude and direction. So what do I mean by that? Let's insert our x and y axis. So I'm going to start at 1, 2, 3, 4, 4 comma 0. I mean 4 comma 1, my bad. That'll be my initial point. And let's have our terminal point be 5 comma 3. So if you look at this, you start at 4 comma 1, and you can think of this vector as moving 1 to the right and 2 up. So move 2 up, 1 right. Now likewise, you can have an initial point at let's say 1 comma 2. And again, we will move 1 to the right and 2 up, which will place us at the point 2 comma 4. And let's draw in the vector. Now if you look at these two vectors, you can see that from the way I've drawn them, because they're the two right angles formed by the sides, sorry, the two legs of the right triangle formed by the vectors as the hypotenuse tells you that they have the same length and they have the same direction. You can see that these two green line segments are parallel. They move in the same direction, and because they're the same right triangle, you definitely know that they have the same length or magnitude. So we would say that these two vectors are equivalent. So I could call this vector over here u. I could call this vector over here v. And whenever two vectors are equivalent, we say that they are equal to each other. So we would say u, the vector u, is equal or equivalent to the vector v. Okay. Okay. So let's talk about some vector operations. So there's something called a scalar operation, or scalar multiplication. So scalar multiplication, what it does is you can think of it as dilating or stretching a vector. So in other words, it doesn't change the direction of the vector. It only changes the magnitude of the vector. So let's say we have this vector u. U starts right here and ends right there. You could extend this vector out in the same direction but have it keep going. So it would still start at this point right here, but it would keep going out, and that new vector could be called v. So because v is a stretched version of u, v is a scalar multiple of u. And the way we write that is we would say u k times u is equal to v. So what we have here is the vector v is a scalar multiple of u, since it has the same direction but changed length. And the way, length, I can't spell length apparently. And the way we write that with an equation is this right here. So if something is a scalar multiple of something else, you can multiply one of the vectors by a number and get the other one. Okay, and what it does is it changes the what's it called? The magnitude by that amount. So let's give an example here. So let's say you have u. The vector u looks like this. And you know that the magnitude of u is 2. So what do we know now about the vector v, which is equal to 3u? Well, u is a scalar multiple, v is a scalar multiple of u. So because these two things are equivalent, we now know that the magnitude of v is equal to the magnitude of 3u. And what happens is the scalar can factor out of the magnitude. Okay, so what was the magnitude of u? It was 2. So you get 3 times 2, which is 6. So the magnitude of v is 6. Why? Because v is simply a scalar multiple of u. It is 3 times u, so it is simply 3 times longer than u. It must have a length of 6. Okay, so you can dilate or stretch vectors by doing that. There is something interesting that happens when you multiply by a negative number. So let's look at what happens when you say v is equal to negative u. Okay, so u is this vector over here, this blue vector. Negative u points in the opposite direction. And so it has the same length, so the magnitude of u over here was 2. The magnitude of v will also be 2, because the magnitude doesn't care about the direction. It switched the other way, so it's still 2. So v, or negative u, points in the opposite direction of u, but has the same length. These both have a length of 2, but they are 180. They point in opposite directions, in other words, they form a line, right? There's 180 degrees between them. So you can also change this up a little. So what if v was equal to negative 3u? Well, you'd point in the opposite direction of u, but you would be 3 times as long. So negative 3u would look like this. So here's u. Negative u points in the other direction. Negative 3u points in the other direction. Is 3 times as long. So in other words, this would have a magnitude of 6. And points in the opposite direction. Okay. So scalar multiplication is pretty straightforward. Let's talk about vector addition. Oops. Let's talk about vector addition. Okay, so if you have one vector u and another vector v and you want to add them together, how do you do this? So equals what? Well, it's going to equal another vector. And we call this the vector sum. But how does that work? So I'm going to draw a picture. Let's say that u looks like this. So u has an initial point right here. And a terminal point right there. Okay, let's say that v will also have an initial point right here and a terminal point right there. So initial point, and then right here, a terminal point. And this is our v. So the vector u plus v, the sum, in other words, the sum, which is the vector u plus vector v, is the vector which starts at the initial point of u and has a terminal point and has the terminal point, sorry, of w, or v. I don't know why I keep on saying w. So what do I mean by that? So here's the initial point of view that I'm talking about. So we have the initial point of view. So now what do I mean by has the terminal point of v? So what I'm going to do is I'm going to draw v at the end of u over here. So these two vectors are equivalent. They have this. You can see that the two green vectors are parallel. They have the same direction, and they also have the same length. And here is that terminal point right there. That's the terminal point that I'm talking about. So the vector u plus v starts right here and ends over there. So this is u plus v. This is called usually it's called the parallelogram method of addition. You start with your u vector, you place v at the end of it, you start right there and you end right there. And there's some interesting things that you can do with this. You can start wondering, like, what does u plus negative v look like? Okay, and we can draw the picture. So let's say u is like this. And let's say that v looks like this. So I'm going to start at this initial point, which I'll mark in red. I go to the end of u, and instead of drawing v, I want to draw negative v, which will go in the opposite direction. And now I get my terminal point right here. So this vector right here is u plus minus v. Notice it has a different direction compared to the example above. Okay. Let's see, how long have we been going for? I just don't want to make this video too long. It has been going for 18 minutes. Okay. Let's do one more example and then we will... Actually, we're going to do one more example and get to components. So what about if you want to do something like u plus 3v? It works the same way. Let's say that u looks like this, and v looks like that. So I'm going to start here at the initial point of view. I go to the end of u, and I've drawn v. But I'm not adding v, I'm adding 3v. 3v is a scalar multiple, so it's in the same direction as v, but 3 times as long. So 3v would look like that. Here is the end point. And u plus 3v would look something like that. Okay, so you'll do some examples. You can see graphically what's going on, where you start at your initial endpoint, you go out to the end of one vector, and then you start adding on whatever scalar multiple you have of the other. Alright, so let's talk about something called the triangle inequality. This should make a lot of sense. So from thinking about triangles, it's where the name comes from. Let's say you have u, and you've also got v. And then now you have a second vector, which is their addition, which is the vector u plus v. So there's three different magnitudes that we have here. There's the magnitude of the vector u. There's the magnitude of the vector v. And then there's the magnitude of the vector u plus v. So you start wondering, well, what's the relationship between these three magnitudes? Like, can they ever be equal? What's going on? So you get the triangle inequality, also related to something called the Schwarz inequality. So what it tells you is that the sum of the two vectors, the magnitude of u plus v, that has to be smaller than or equal to the magnitude of u plus the magnitude of v. And if you think about this, this should make sense because a straight line is the shortest distance between two paths. So a straight line is the shortest distance between two paths. Or sorry, between 2 points. It's the shortest distance or path between 2 points. So let's call this point right here A, and let's call this point right here B. Well, the vector u plus b is a straight line between A and B. That has to be shorter than any other path you can take. You could start at A and travel along u, and then travel along v and get to B, which is following this and then this. But that isn't a straight line path because you go along u and then you go along v. That has to be longer than the straight line path between them. Okay, and that's all the triangle inequality says. Okay. So let's talk about something called vector components or component form. So the easy way to think about this is by looking at two equivalent vectors. So let's look at the vector which starts at 1, 2 and ends at 2, 3. Like so. And let's also look at the vector which starts at 3, 4 and ends at 4, 5. Okay, let's call this one V. Let's call this one U. Okay, you can tell that U and V are equivalent. Why? Because you start at the initial point, you go 1 right, and then you go 1 up. You start at the initial point, you go 1 right, and you go 1 up. U and V have the same direction and magnitude. They also have something that's called the same component form. You can think of the component form as the directions which take you from the initial point to the terminal point. So U is the vector which moves 1 right and 1 up. So when you write component form, you put these braces around it. That's also what V does. It starts at the initial point and goes 1 right and 1 up. So you can think of it as X and Y values. Right? This one tells you, the first number tells you about movement along the x-axis. The second number tells you about movement along the y-axis. Okay, so it's pretty straightforward to figure out what the component form is. If your initial point is x1, y1, and your terminal point is x2, y2, and this is your vector u, then the components of u are going to be x2 minus x1. Oops, x2 minus x1. And y2 minus y1. In other words, you take the terminal value minus the initial value. And this should be pretty familiar from like Algebra 2, because you get a right triangle. This point right here is x2 comma y1, and you can figure out that this length is y2 minus y1, and this length right here is x2 minus x1. In other words, if you start at the initial point, you move right by that amount, and then you go up by that amount. Okay, so we call that the component form of a vector. If two vectors have the same component form, you get they are equivalent. Let me move this down a little. There's some other stuff that we can talk about here. It's pretty easy now to come up with a formula for the magnitude, because we have like a triangle here. The magnitude of your vector is just going to be, you're going to take your x component, and you're going to square it, and you're going to take your y component, and you're going to square it, and you're going to take the square root. So if your vector u has components x, y, just take those x and y components, square them, add them together, and take the square root. Why? Because your vector u, you start at some initial point, you move x by this amount to the right, you go up y, that gives you your terminal point, and you can see that, well, this is your u vector right here. That's the hypotenuse of this right triangle, right? So you just take this, you use the Pythagorean theorem to get there. Pretty straightforward. Okay. We also need to talk about scalar multiplication and component form. Sorry, I just need to make more space. So how does scalar multiplication play with component form? So if you have some u vector with components x, y, again, you're starting here at your initial point. You're moving to the right by x, and you're moving up by y. That gives you your terminal point, so you're going from there to there. So what would happen, for instance, if you wanted 2u? Well, we know that that's a scalar multiple. If you're multiplying a vector by 2, it doubles the length. So let's double that length. Right, here was your u. There's another u. So you would have to start right here at the blue. That would be your initial point. And you need to end right here at the red. That would be your terminal point. And this is actually not that hard to do. What you could do is, instead of just going the length x, you can double your length and go 2x. And instead of going up y, you double the length and go up 2y. Okay, so doubling a vector with component form is pretty straightforward. You're going to have 2 times the component form. And you just distribute it in. You get 2x, 2y. Pretty straightforward. Okay, what about vector addition in component form? Also pretty straightforward. Okay, sorry. I didn't mean to make it go down that far. Okay, there we go. That's a little better. So what about vector addition and component form? Okay, so let's say you have a vector u, which is x and y, and then you have some vector v, which is length a and b. Okay, so let's draw our u. So here's our u. We know that the way this works is you first travel x to the right, and then up by y. Okay, what about our vector v? Let's say it looks like this. So we'll draw v right here at the endpoint. So we know that the way v works is you first travel right by a, and then up. Actually, let's not make it. Let's make that look a little different. This looks really ugly. Let's make it look more like that. There we go. That will be v. So we add it over here. Parallelogram rule. First go right by a, and then up by b. So your resulting vector will start here at the white and end at the white. That's going to be u plus v. And notice what you can do is start down here at the bottom. First go x, and then go a, then go up by y, and then go up by b. So adding them is pretty straightforward. You add the components. U plus v will quite simply be equal to x, y, plus a, b, right? That's the component way of writing it. And then you add the x components. You get x plus a, oops, comma, you add the y components, y plus b. Boom, there's your component form for the sum. Okay. So the last topic we're going to get to here are something called unit vectors. Unit vectors have a magnitude of 1. So how do you know that v is a unit vector? Well, v is a unit vector if its magnitude quite simply is 1. In other words, it has a length of 1. And we're going to talk about something called the normalization of a vector. To normalize a vector means you take that vector, you want a vector which is in the same direction as it, but only has length 1. So let's make this up a vector. Let's say that you have some vector u, and the magnitude of u is 5. So let's say u starts right here and ends right there. All right, there's your u. Well, u has length 5. 1, 2, 3, 4, 5. You could scale u down. What I want is this vector right here that starts here and ends right there. I want something that's 1/5 the length of u. So I'm going to make a new vector called v. I'm going to say v is 1/5 of u. Now when we go and we calculate the length of v, we're going to get the length of 1/5 of u. The 1/5 can be factored out. The length of u is 5. And what's 1/5 of 5? Well, that would be 1. V has a length of 1 and is in the same direction as u. So if you want to normalize a vector, it's pretty straightforward. So to normalize some vector u, what you're going to do is take the vector u and divide it by its magnitude. All right, that's what I did right here. I knew that u had a length of 5, so I multiplied it by 1/5, which is equivalent to dividing it by 5. That gave me a new vector in the same direction, and it was scaled down. Okay, now you might be wondering, like, why are we curious about these unit vectors? It's because they're actually related to components. So I'm going to have the vector, I'm going to talk about two vectors. They're both going to start at 0, 0 at the origin. So that will be my initial point. One of my vectors will have a terminal point at 1, 0. The other vector is going to have its terminal point at 0, 1. This vector from 0, 0 to 1, 0, I'm going to call I, with a little hat on top of it. And the vector which starts at 0, 0 and goes to 0, 1, I'm going to call J. So I, in component form, it goes 1 to the right and doesn't change the y value. Notice that has a length of 1. The magnitude of 1. Remember, you could take the square root of the x component squared plus the y component squared. That's the square root of 1 squared, which is 1. J, the unit vector j, does not change the x value, it only makes it go up by 1. So when you take the magnitude of that, you get 0 squared plus 1 squared, which again is square root of 1 squared, which is 1. They're both unit vectors. And this gives us an interesting way to rewrite components. So as an example, let's say you have some vector u, which is equal to 5, 3. I can split that up into the vector 5, 0 plus 0, 3. Right? If you add 5 and 0, you get 5. If you add 0 and 3, you get 3. And then with the scalar multiple rule, for the first vector, I can factor out a 5. So I get 5 times 1, 0. And then I could factor out a 3 for the other one, and I get 3 times 0, 1. And notice, 1, 0, I have a name for that. That's called I. And 0, 1, I have a name for that. That's called j. So you can see quite clearly that the first number from the component form is what I is multiplied by. And the second component, the 3, is what j is multiplied by. Okay, so we can think about, we're going to use this later. There are many different ways to represent vectors. You can represent them in components, like we have right here. Or you can represent them as a sum of unit vectors, which we have as like right here. Okay, and we're going to explore this as we go on about why you might want to do these things. Okay, and that is the end of the video.